Welcome to the 6th lecture in abstract algebra. The topics that we'll explore in this lecture include vectors in finite dimensional real space and an introduction to vector spaces. Okay, so last time we looked at vectors as special types of matrices. This time we'll look at vectors as objects distinct from matrices, and in particular we'll be looking at column vectors. And there's some simplifications we can make to notation. State this as a remark. A column vector V with n real components which in the language of matrices we say that it is an n by 1 matrix with real entries, is denoted more simply as a vector in n-dimensional real space. Now, if we list its components, we can use the convention of listing the components horizontally versus vertically. So it has components v sub I, or v1 through vn. And in this lecture, I am going to use angled brackets for the components of a vector to distinguish it from a point. The vector v has both a magnitude, which we will call the norm of the vector, and this corresponds to the length of the vector, and a direction. So we represent vectors in space as directed line segments or directed arrows. So new definition. To each point P in n-dimensional real space, these points is an ordered n-tuple. That is, it has coordinates x sub 1 through x sub n. To each point in n-dimensional real space, there corresponds a unique column vector, which we'll call R, in n-dimensional real space, called its position vector, whose coordinates are identical to the whose components are identical to the coordinates of the point. That is, the position vector R for the point P with coordinates x sub 1 through x sub n is the vector with components x sub 1 through x sub n. All right, so we'll look at an example. We'll look at the plane. The point 3, 2 in the plane has the position vector r, where that position vector r has components 3, 2. Now, recall from geometry that a point is a location in space, and it does not have a dimension. That is, it has no magnitude. There is no length, width, or height associated with a point in space. It is a dimensionless object, whereas a vector has a magnitude. It has a length and a direction. The length in this case is given by the Pythagorean theorem. The length in this case is the square root of 13. And the direction is encoded in the component form of the vector. We read off from the components that we move in the positive horizontal direction 3 units and in the positive vertical direction 2 units. Or we can specify the direction by giving an angle with respect to the horizontal axis or with respect to the vertical axis, whichever is more convenient. But it's standard to give, for vectors in the plane, to give the direction as an angle with respect to the horizontal axis. Now, the 0 vector is the special vector that has as its components all zeros and has 0 magnitude. And it's the only vector in n-dimensional real space for which this is true. Now, a vector in n-dimensional real space that originates at the origin is said to be in standard position. So again, we'll look at the example. Let the vector v be the vector 3, 2. So this is a vector in the plane. If the vector begins or originates at the origin, then it is the same as the position vector for the point 3, 2, but a vector need not originate at the origin. It can begin at any point in space. So if we begin at the point 0, -3, then the vector terminates at the point 3, -1, but this is still the vector v. It has the same length and is moving in the same direction. Also, if we begin at the point -3, 0, then the vector v terminates at the point 0, 2. Again, this is the vector v. So a vector is distinguished from a point in that it has a magnitude, it has a length, and it is not necessarily tied to a given location in space. It can originate from any location in space, that is, from any point in space. But if the vector begins or originates at the origin, then it is said to be in standard position, and in that case, it is the position vector for the point, whose coordinates are equal to its components. All right? Okay, so given 2 points in n-dimensional real space, so P1 has coordinates x sub 1 through x sub n, and P sub 2 has coordinates y sub 1 through y sub n. The displacement vector from the point P1 to the point P2 is the vector whose components are the difference of the coordinates of the 2 points. The terminating points, the terminating coordinates minus the originating coordinates. So we have y sub 1 minus x sub 1, and so on, up to y sub n minus x sub n. An easy way to remember how to compute the displacement vector is head minus tail. That is, again, we take the coordinates of the terminating point and subtract the coordinates of the originating point. So let's look at an example. Let the point P1 be the point -3, 0, and let the point P2 be the point 0, 2. Then the displacement vector from P1 to the point P2 is 0 minus -3 and 2 minus 0, and this is the vector 3, 2. So notice that the position vector of the point P, having coordinates x sub 1 through x sub n, is the displacement vector from the origin to the point P. So we have the displacement vector from the origin to the point P, and this is x sub 1 minus 0, and so on, up to x sub n minus 0. And so this is the point P. It has the position vector, rather, for the point P, that is x sub 1 through x sub n. All right? Let U and V both be vectors in n-dimensional real space. And let C be a scalar, let it be a real number. Then the vector U is equal to the vector V if and only if each component is the same in both vectors. And so here we have vector equality. The component in the sum or difference of two vectors is the sum or difference of the components. And so here we have the definition for vector sum or difference. And the component in the scalar multiple of a vector is the same as the scalar multiple of that component. So two vectors are equal if and only if they have the same components. We form the sum or difference of a vector, of two vectors rather, by taking the sum or difference of their components. And we form the scalar multiple of a vector by taking the scalar multiple of each of the components, multiplying each of its components by the scalar. Now, an important fact to recognize is that the vector minus v has the same length as the vector v, but has the opposite direction. Right? Again, let u and v be vectors in n-dimensional real space. The dot product or another name for it is standard inner product of the vectors u and v is the real number. That is, it is a scalar, which we denote u dot v. And this is the sum of the products of the components. So notice that the dot product is commutative. That is, it does not matter the order. U dot v, again, is the sum of the product of the components u times v. This is the same as the sum of the product of the components in the order v times u, and this is v dot u. All right? New definition. Let v be a vector in n-dimensional real space. The norm of the vector v, the norm is also called the magnitude or length is the real number. Which we denote using the symbol for the vector with two vertical bars on either side. This is the square root of the sum of the squares of the components. So notice that the magnitude of a vector is the square root of the dot product of the vector with itself, or equivalently, the dot product of a vector with itself is the square of the norm of that vector. Notice also that the norm of the vector v is the same as the norm of the opposite of the vector v, because the two vectors have the same length but opposite directions. So now we come to our first theorem. Let v be a vector in n-dimensional real space, and let c be a scalar, a real number. Then the norm of the scalar multiple of v is the absolute value of the scalar times the norm of the vector. whoops, we need to prove this. So we know that the square of the norm of the scalar multiple is the dot product of the scalar multiple of v with itself. This is c squared times the dot product of v with itself. So the norm of the scalar multiple is the square root of c squared times v dot v. This is the square root of c squared times the square root of v dot v. The square root of the square of a number is the same as the absolute value of the number, and the square root of the dot product of the vector v with itself is the norm of the vector v. So the norm of a scalar product of a vector is the absolute value of the scalar times the norm of the vector.